Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video, we will learn how to calculate combined stress. Any member in real life is subjected to different types of loading: bending moment, twisting moment or torsion, transverse shear forces, axial forces, and today we learn how to calculate the combination of these stresses inside the material. Let's start. Consider a beam, simply supported beam. Again, that is subjected to uniform distributed force and also a tense axial force. For example, here, 200 axial force, which is 200 kilonewton, a uniform distributed force intensity, 30 kilonewton per meter, a span of the beam, 3 meter, and its I-beam cross sections is S 250 times 52, which is 254 mm. This is 125 mm. This thickness and this thickness, flange thickness, and is equal to 12.5, and the web thickness is 15.1 mm. Total height, depth of the beam is 254. A area of this beam is equal to 6.65, 10 to power minus 3 meter to power 2, and also I for this beam is 61.2, 10 to power minus 6 meter to power 4. Neutral axis, yeah, which is symmetric. If we consider this as accurate number is 126 according to tables. Okay, that's the information for the cross section. What happened? This beam is subjected to different types of loading: uniform distributed load and axial load. But uniform distributed load produces bending moment in this beam, and if you draw the bending moment diagram, you will find such a curve. And because we consider only the worst case scenario, and worst case scenario is when the bending moment is maximum, and maximum bending moment here occurs at the middle of the beam, which is 1.5 meter, and max. And this max, if you calculate it, is equal to 33.75 kilonewton meter. How to calculate it? You have to draw free body diagram. You have to write the equations of bending moment that you learned it already before. And then this value, you can reach to this value. Or another method is just consider, because the loading condition doesn't change through the beam, just as uniform distributed load, we can consider a length of the beam which is x under uniform distributed. And then if you calculate the reaction at the support A and reaction at the support B, we have this load divided by 30 times 3 is 90 divided by 245 kilonewton. And this one also, sigma fx equal to 0 is equal to 200 kilonewton. Then here we have the shear force and bending moment at the cut sections and summation of moments above the cut point C equals to 30 times x times x2 and 45 times x. 45 times x is clockwise. We consider it actually negative, minus 45 times x. And then this 30 times x over 2 is counterclockwise positive, 30x times x over 2, and m counterclockwise positive equal to 0. Then m is equal to minus 15x2 plus 45x, and at x is equal to 1.5, you will reach the value 33 point at the middle of the beam. Or if you want to find the maximum, you have to take the derivative with respect to x, and it's minus 30x plus 45 equal to 0, and x is equal to 1.5 is the maximum bending moment that can happen. Okay? Then value of m, which is called m max, is equal to 50 times 1.5 to power 2 minus 45 times 1.5 is 33.75 that we wrote already there. This is how to calculate bending moment diagram. I don't want it to mention that, but maybe this is a question how I reach to this value for bending moment, maximum bending moment. Then M max 33.75 kilonewton meter. Okay. Stresses due to this worst case scenario, which bending moment is maximum, is equal to sigma max, which M must be max, Y must be max, and M is 33.75, 10 to power 3 Newton meter. Y max is this now, 254 divided by 2 times 10 to power minus 3 meter. And I, 61.2, 10 to power minus 6 meter to power 4. And you reach the value which is equal to 70.037. 10 to power 6 Pascal. Or you can call it 70.037 megapascal. I write it here. Due to bending, worst case scenario sigma is equal to 70.037 megapascal. Just have this value. The other things that we have is the beam under, I draw the beam 200. There should be a axial force also 200 kilonewton here. M was here. Shear force downward was here. Distributed load was here. Then the only thing that I have here to calculate axial stress due to 200, which sigma is equal to the force 200 and to power 3 Newton divided by the area with 6.65 10 to the power minus 3 meter square. And that's it equal to 70. That's the bending moment, 30.075. 10 to the power 6 Pascal. Or I can write it that sigma, this is due to bending. This is due to axial load. 30.075 megapascal. The story starts here. I have these two types of stress inside the material. Okay. How I calculate it is belongs to the previous courses that I showed you. Then I show the distribution of these stresses inside the material. Consider them step by step. Assume that we draw the cross sections of the material as a line. We just rotate it like this. I consider it as a, just if I show it as a, and show the cross sections of the beam. Actually, this IB, I show these cross sections as a line and show the distribution of stress due to bending moment here. Because it is compressed at the top, we have compressive stress here and neutral axis 0. And this amount is 70.037 megapascal. And here in the bottom flange, we have a tensile stress, axial tensile stress, which is the same one. This is neutral axis. For the axial loading, again, I draw the cross section, this surface, and show it as a represented as a line. And I have 30.075 megapascal uniform through the section of the beam. Okay, what happened inside the material? This axial stress inside the material combined together. And what's the result? Show it. Another cross sections. These two, this is compressive negative. You consider this is tensile positive. Then when you add them together, it should be, because it is larger than this, something like, you can say 39.70.037 minus 30.075, 39.9. That's heavy, compressive. And here, what we have, it is 70.37 plus 30.075. It is 100, around 100, because both are tensile in the bottom. Exact value is add them together, you got 100.79 megapascal. What happened to the neutral axis? Neutral axis move up. How much? You can calculate it. This amount, compressive stress, in some places are equal to 30.075. They neutralize each other. That's the new neutral axis for the combined stresses. How I can find that? How exactly at what point of the cross section this stress is zero, combined stress is zero? Very easy. You can say that P over A must be equal to my over I. Y is the distance from the neutral axis, and we can find out. Then P is 200, 10 to power 3. A is 6.65, 10 to power minus 3. M, we found that M was 33.75, 10 to power 3, times Y, we are looking for that, divided by I, 61.2, 10 to power minus 6, meter power 4. Then this is Newton, this is meter square, this is Newton meter, and this should be meter if you calculate. Then you reach to this point that Y is equal to 54 millimeter, or 0.054 meter, or Y is equal to 54 millimeter. 54 millimeter from neutral, previous neutral axis of the bending. You go, no, how much is it here? From top, you must subtract this distance, which is 254 divided by 2, 127. 127 minus 54 is 73 is this amount here. From here to here, 73 millimeter. That's the new neutral axis. That's the distribution of stress inside the material. That is, and this 54 was the distance between these two previous and the new one current neutral axis. Neutral axis for bending only, and neutral axis for the combined stress. You will see the worst case scenario happens in the bottom flange, that is under bending stress plus axial load stress. If this axial load is compressive, it is exactly vice versa. Neutral axis move to down, and the compressive stress is the worst case scenario for this. Is not actually what happened inside the beam. Because of this distributed load, we have also shear, horizontal shear stress inside the beam that we consider it in another video. Thank you for watching, and see you in the next video.